Welcome to Mrs. Mahoney's podcast. This is our second one in Unit 9. We are at the top of page 3, and the last couple days we've been looking at kind of the theory and the relationships behind pressure, volume, and temperature. And as you've expected, yes, there's going to be some math that goes with it. So today we're going to kind of look at the math and how we're going to put a relationship, and is there a mathematical formula that works? And the answer is yes. So it is math. So you're going to need calculators. You're going to need that formula chart. You can probably get by today without the formula chart because I've got it written for you, but whenever you have a test, you're going to realize there's a lot of really good information on that formula chart. So let's look at these units we're going to be using, and these are the ones you need to get very comfortable and familiar with. So the first one we're going to talk about is pressure. Okay, pressure. Where does this even come from? Think about the air all around us, and when you looked at the lab yesterday, realize that there's actually a lot of pressure going on around you. All those air molecules, the nitrogen, the oxygen, they are bombarding. So what they originally did is they had this column of mercury, and the air pressure coming down forced the mercury, this is an open-end tube, up into it, and the height, right here, the height of this mercury is what they measured as a standard pressure. So, but it came from the air molecules pushing down on that. They used mercury because it's about 13 times more dense than air, than water, 13 times more dense than water. So if they'd had a column of water instead of just mercury, it would have had to be 13 times taller. Not very practical. So history, that's where this kind of comes from. This is hence a pressure, a unit of pressure, millimeters of mercury. That was the standard height at sea level that the air pushed a column of mercury. That's why it's a unit of pressure. So if you see something labeled millimeters of mercury, you know it's a pressure. Okay, another more common one we're going to use, ATM, okay, not a cash machine. That stands for atmospheres. 1 atmosphere is 1 ATM. Again, sea level. These are standard pressures. Okay, the next one that you're going to be seeing is KPA, stands for kilo pascals. So it's 1,000 pascals. Again, named for a scientist. These are the most common. Now, I did kind of put in the American PSI. What does that stand for? Pounds per square inch. Pounds per square inch. And again, it's all talking about how many times those molecules are hitting the side of a container. That's what pressure is. So part of doing these problems is to recognize the label. The label is telling you what the unit is. ATM, pressure. Millimeters of mercury, pressure. KPAs, pressure. Okay, the other units we're going to be using, volume. Let's just go ahead and add that. These are more common, probably why I didn't put them down. Most common, milliliters or liters. Okay, sometimes they might throw in a centimeters cubed or a meters cubed. Most common, liters and the milliliters. Okay, temperature. Key thing, highlight this, color this, whatever you have to do to get this to stick in your head. To do calculations, they have to be in Kelvin. They have to be in Kelvin. They have to be in Kelvin. Kelvin is a new scale. The nice thing about this, we don't have those weird conversions that go in Fahrenheit to Celsius. Those are just bizarre. I can't even tell you it, I'll be honest. But to go to Kelvin to Celsius, that one I can do. The reason 1 degree Kelvin is going to be equivalent to 1 degree Celsius. The change is going to be the same. So the size difference is the same. Why do we have Kelvin then? What's the reason? Big, there's no negative numbers. So there's no negative values in Kelvin. So Kelvin is based on what's called absolute zero. This is a theoretical temperature that all particle motion would stop. Okay, there's some debate. Definitely there's some people who have said it's gone colder at this point. We're not worrying about that right now. We're just going to say, okay, 0 Kelvin is known as absolute zero. That's the temperature when all theoretical particles would stop. It is equivalent to negative 273 degrees Celsius. Yes, that's very, very cold. Key thing, there's no negative numbers. That's why we use them in all gas law calculations. So that, though, this right here makes this conversion really, really easy. All you have to do is whatever the Kelvin temperature is, to find Kelvin, take your Celsius and add 273. If you want to go from Kelvin to Celsius, then you're going to subtract 293. So here's 25 degrees Celsius. How do I go to Kelvin? Take 25 and add 273, and what do you get? 298 Kelvin. This, you might want to make a little note, this is room temp. This is why this shows up a lot in problems, because traditionally room temperature is about 25 degrees Celsius, which is about 72 degrees Fahrenheit, which is usually considered a room temperature. So this is why this will show up a lot. Okay, so look at this. Negative 40, what is that in Kelvin? Add 273, that's 233 Kelvin. 200. Okay, now we're going to have to subtract because it's Kelvin to Celsius. So subtract 273. So 200 Kelvin is minus 73 degrees Celsius. Okay, I'm going to leave these other three for you to do, but all calculations must be Kelvin, must be in Kelvin, must be in Kelvin. Okay, on your formula chart, you're also going to notice that there's a standard temperature and pressure. So a lot of times problems are going to say at STP. At STP, what is the volume? Okay, that's a known condition. This is on your formula chart. STP is 0 degrees Celsius or 273 Kelvin, and what's considered sea level, which would be 1 atmosphere, which means it's equivalent to 101.3 kPa or 760 millimeters of mercury. Very useful. You don't have to memorize. Realize STP, standard temperature and pressure, means something. It's written on your formula chart. It just gives you a temperature and pressure. Okay, so here is a formula that's your new best friend. You don't, again, have to memorize. This is on your formula chart. This is why on all the tests, I will make sure that you have both of your formula charts. Okay, this is the whole thing together. It's again called the combined gas law. P, pressure, volume, N is moles. So make sure you know what all of these are standing for. P is pressure. V is volume. N stands for number of moles. That's why it's N and not M. Okay, T is temperature, and again, it has to be in Kelvin. In Kelvin. That's the only one that you're going to have to make sure is in Kelvin. Pressure, as long as they're the same, you don't have to change them. Volume, same thing. Typically, they're going to be in liters, but as long as they're in the same volumes and cancel out, they don't have to change them. Temperature has to be in Kelvin. Even if both temperatures are given in Celsius, you still have to change them both to Kelvin. You have to, you have to, you have to. Okay, the nice thing about this formula, at one point I used to tell you each of them separate, because if you cover up this bottom part, cover up N1, T1 on both sides, and you have P1, V1 equals P2, V2. That's Boyle's law. If you cover up the P over N, you get volume over temperatures. That would be Charles' law. We could cover up the volumes and the moles, and that would be Gay-Lussac's law. You have all the laws here, so the key thing is ever something in your formula does not change, and pretty much if they do not mention it, you're assuming it does not change. Cover up those variables, cross out those variables, realize those variables will not be included. So by using one formula, we can really realize we can do all the problems that we need. I call these plug and chug, meaning you're going to have to write out the problems, write out your variables that you know, plug them into your formula, and you let the calculator chug them out. Or, as Mrs. Fisher says, crank them out. I guess that makes her older than me if she's using a crank calculator, because I chug them out. I don't crank them out. So this is how I expect you to see them. And yes, when you have your quiz on Thursday, this is what I'm looking for. You show me your work. So when I'm reading through this, I just start labeling everything. Okay, so initially I have a pressure of 12 atmosphere. That's what these ones mean. Ones are initial, So think of ones as like an initial. 2 can be a final. So you're getting one gas and you are changing its conditions, and we want to see how it changed. So as I'm reading through that, if that was initial, that is telling me what my 12 atm is, my initial pressure. And a volume, so that means my V1 is 23 liters, and a temperature of 200 Kelvin. Okay, it's already in Kelvin, so I'm good. Then I raise the pressure. That means I'm changing pressure, so that's my new pressure, to 14 atmospheres. So I'm increasing the pressure, and it says that I'm going to increase the temperature. What is happening to my volume? So I have 6 variables here. Notice, what did I not talk about? We didn't talk about the end, so that means I'm going to ignore it. I'm assuming I have the same gas. I'm not changing the amount of gas, so I don't even have to worry about the moles in this problem. So what do? I look at my formula up there. So I know I have P1 V1 over T1 equals P2 V2 over T2. So what am I going to do? I'm going to plug in my variables. What is my P1? That was 12 atmospheres. What was V1? 23 liters. What is my T1? 200 Kelvin. On the other side, what's my P2? 14 atmospheres. V2, that's my unknown. That's my X. I do not know it. What else do I know? 300 Kelvin. Now it turns into an algebra problem. Okay, now this is why we practice these. You need to figure out algebraically how do you solve these. Some of you like to do all of this, 12 times 23 divided by 200, write down a number, and then you say 14 divided by 300, write down the number X. I like to do it all at once in my calculator. What I just plug in my calculator is 12 times 23 times 200, then I cross this over, times 300 divided by 14. Algebraically, you find what makes sense so that you do the math, and you would get 29.6 liters. Okay, looking at significant figures, we're keeping everything just in whole numbers. I'm not going to stress on sig figs right now, keeping everything in whole, but if I want to go to a whole, I could say 30 liters. Right now, I want you getting comfortable with math, realizing those significant figures is the last thing we're kind of look at. Okay, let's just do a couple more. So, same thing. I want you to write the variables. So just read the problem. You come into a number. What is that? So a gas takes up a volume. So that must be my V1 is 17 liters and has a pressure of 2.3 atmospheres and a temperature of 34. But look at that's degrees Celsius. First thing I'm going to do so I don't forget, change it to Kelvin. Add 273, change it to Kelvin, change it to Kelvin, change it to Kelvin. So that's 307 Kelvin. Okay, so if I raise the temperature, so that means I know my new temperature is 50 Celsius. I'm going to change it to Kelvin right away so I don't forget. That's 323 Kelvin. What else do I know? Lower the pressure, so I give me a P2. 1.5 atmospheres. This one's also asking about volume. They're not always going to be about volume, but I will have to be given enough information to solve the others. So what happens now? Plug. So I know 2.3 atmospheres. That's a P1. V1, 17 liters. T1 has to be 307 Kelvin. P2, 1.5 atmospheres. V2, that's again my unknown. T2 is 3 Kelvin. And again, mathematically, find a way, make sure you're solving it in your calculator that you get the same answer as 27 liters. Okay, so let's kind of look at the others. I want you, looking at this, I want you to try this. What answer should you have gotten? You should have gotten, as your answer, 2.5 atmospheres. Try that. Let me know if that's what you got. And we're going to, again, this is what we're going to start with the next day. Next day being Wednesday. Okay, let's look at number 4 because this one's just a little bit different. Because if I'm going through it, a gas has a temperature of 14 degrees. Okay, so that's a temperature. First thing I do, change it. Because I just do that automatically because it's really easy when you start plugging in to have forgotten this. So when I write it down, if it's not in Kelvin, I automatically change it. What else do I know? I have a pressure of 4.5 atmospheres. Okay, I'm going to change my temperature. So this is going to be my new temperature to 29. Again, what do? 273. So I add 273, and this is going to be 302 Kelvin. And it's saying, okay, what is my new pressure? So notice in this one, my volume did not change. So that means when I'm looking at this formula, if I still on the formula chart, I have this whole formula. P1, oops, these are V2s, excuse me, T2s, these are all should be 2s, and there's an N2. What did not change? Moles didn't change, and volume didn't change. So really, what is my formula I'm working at? P1 over T1 equals P2 over T2. Looking at this is that direct relationship. So these are the ones, it's really easier when I don't have that third variable or not all three changing, I can check my work. Because I know that if my temperature is going up, my pressure better go up. We've looked at that and we've seen that relationship. But let's mathematically prove that. So let's plug in what I know. What is my first pressure? 4.5 atmospheres over my 287. And what is that equivalent to? Well, I don't know my pressure, but I do know my temperature raised up to 302 Kelvin. Cross multiply. All I have to do is cross over, bring this over. So 4.5 times 302 divided by 287. And what does your pressure do? It goes up to 4.7 atmospheres. Does that make sense to me? Yes, my temperature went up. I expect my pressure to go up. That is also what that showed. Okay, so let's try, I want you to try number 5. Your answer should be 47 liters. You can try number 6. Number 6, now your answer should have been like 11,300 liters. That technically, okay, we want to look at significant figures, probably 11,000 liters, but to get to where it's kind of close. Okay, 7, try those two. 7 and 8 we'll kind of do together. I'm going to probably pick some of you to do them on the board. Just saying, be ready to try these. This is the math. These are called the combined gas laws. This is what your quiz is going to cover on Thursday, and is what we're going to work on all day tomorrow in class. You need your calculator. I will see you tomorrow.